So let's start. So today's topic is linear discriminant analysis and it is presented by Kundan Kumar. So let's start. So we will be going to discuss linear discriminant analysis for two classes and then linear discriminant analysis for C classes. Okay, next this is just a is it just generalized form of above for two classes. Okay, so first we have to understand what is the objective of LDA. So objective is to perform dimensionality reduction while preserving as much of the discriminatory information as possible. So first time it is not very much clear just listening to this. So we would start by listening to this graphically. Let's see this graphically. Okay. So once again read this bit carefully. So here the objective of LD is to perform dimensionality reduction while preserving as much of the class discriminatory information. So we will perform dimensionality reduction, okay, and we have to also preserve class discriminatory information. So what will this mean? So here you could see we have some classes. We have two classes and data points. So we have to perform first thing dimensionality reduction. This data is in 2D. So after performing dimensional reduction, it will go into 1D. So this is first step, dimensional reduction. Second step, we have also to maintain class discriminatory information. So what is class discriminatory information? So here you could see some data points belong to this group and some belong to this group. Okay, we have to keep these both classes separated. Okay, suppose this is the axis where we will be performing our dimensionality reduction, or we could say we will be taking projection of our data points on this axis. So here you could clearly see that the points are the data points have been reduced their dimension, but both groups got mixed. They are not separate. We could notice here that we have overlap between these groups. So this is not what we want. We want that class discriminatory information should be retained as much as possible and dimensionality reduction. So here we could do that. We should change this axis to some other axis, and we will try different possible lines, and we will take the best line. Okay, so here is another line where we will try to get the projection and retain class discriminatory information as much as possible. So here you could see that dimensions is reduced and also dimension reduced, and both classes are separate. There is a good gap between those classes. So in future, if we have to classify a new data point into any of these classes, it would be easy for us. And one thing is to notice that as much as this gap increases, it will be I mean gap I mean that by gap I mean that gap between both of these classes. Okay, so now you have a basic idea about what LD will be helping us to do and why we have to do this. Okay, so the next thing is to see some terminologies related to this. Okay, so what will be some terminologies? So these are our data points. These these are our data points, and we have to, okay, these are our data points, and we have to uh, perform LDA on them. So what we will be having is that what we will be having is that this line, we will call this line as W. So W is just a unit vector along this line, okay, and it will be helping us to project these data points onto that line. Okay, so coming to next page, uh, we are going to perform LDA on two classes. So first of all, assume that we have a set of d-dimensional samples. You know what means d-dimensional samples? We in total we have n data points, okay, but each data point is a d-dimensional sample. I mean that we could write x1 as a1, a2, ad. This is a d-dimensional subspace, okay, and among these sample points, n1 samples belong to c1 class, okay, n1 samples belong to c1 class and n2 belong to c2, and it is obviously n1 plus n2 equal to n. Okay, so I have already told that W be a unit vector onto which data points are to be projected. So what we will be doing, we will be X is a set of our initial data points. These all combine to make X. Okay, X is a matrix and we can work on it. Okay, so WT will be a projection matrix. What it will be doing? These are X. W is a projection matrix which will operate on X and it will give us this data in new dimension. Okay, and this is Y. We will write as WTX. Okay, let's move on. So in words, above equation projects X along W and we obtain Y. Here notice that, okay, so X and Y both have their own feature spaces. Okay, so feature spaces, I mean that dimensions of X and dimensions of Y are both different from one another and both have their own feature space. Okay, so now finding the best projection vector. How we will find the best projection vector? So measure of separation between the projections. So what do you think that will the best measure to find the best projection vector? What we should do? Okay, let's try viewing this. Okay, so here we will try to see what is the best thing to do. Okay, I say I propose something that this data points of this class has some mean mu1, data point of this class has some mean mu2. I propose that in the new reduced dimension, you will try to increase distance between these means. Okay, the projection of these means, the projection of these means, let this is mu1, this is mu2. I will try to increase the distance between these two so that we have a clear separation between them. Okay, this is my first proposition. So here what we are doing, trying to use separation between the projection. So I am saying let's first try on both of their means to increase the distance. So let's try to increase distance in both the groups. This could be done by increasing distance between mean of both the groups in new projection. Okay, so let's see this. What is this new projection mean here? This this mu1, this mu2, these are the means of data points in the feature space of X after reduction, the new mean of those data points. Okay, so these are data points in Y. Okay, now in reduced dimension. So these means of those data points are said to be in feature space of Y. Okay, so what we are doing, we are trying to increase the distance between these two means. We can't change these two means. We have to increase the distance between these two means. Okay, in new projection. So in new projection, we are going to increase the distance between means. So let mu I be the mean of class Ci in feature space of X. Basically, we are talking about mu1, mu2. Okay, and mu I dash be the mean of class Ci in feature space of Y. Okay, by figure, you could see it like, we are saying it like this. These means are in feature space of X. These means are feature space. These means are in feature space of Y. Okay, we are talking about them. So now we all know formula for finding mean. Mu I, for mu I dash. We will be finding this by adding elements of Y, of course, in a particular class. Okay, and then averaging it. So by putting Y value, in last slide you could observe we have wrote w y as we have wrote y as wtx. So here we will be putting it, and then w2 wt mi. So there is no problem in this. Easy maths. Now we could choose the distance between the projected means to be our objective function, as we were discussing earlier. First we will try to increase the distance between both the data sets. And what we will be doing, how we will be doing, we will doing it by increasing the distance between both the means of both the data classes in reduced feature space. Okay, so this is our objective function, and we will substitute values. So now the new value of our objective function is this in terms of w. Oh, there's a slight mistake. This will be wt. Okay, so moving to next slide. Okay, let's suppose that this is the already find out result. I am just giving you the what will happen if we are going to maximize this objective function. So the result would be something like this. Okay, we will be left with two options, that where we should choose our data. So suppose these are our data points. Okay, if these are our data points, if these two are data points, okay, so the axis has larger distance between means. So if we project these both data points on this axis, okay, so if we project both these data points on this axis, it is for sure that we have the maximum distance between the both means. But there is a problem. Both data points are now mixed in this region, and we do not want. We also wanted to preserve as much as discriminatory information between both data points. But suppose we projected on this axis, then what would happen? We will definitely have less distance between both means, but here we could see that the separation is better. Okay, so this is its most point, and it's, I think this. So here the area of intersection is very less. So this is better class separability, and here we have better class separability, and here we have larger distance between means, and we want best of both of these worlds. Okay, we want larger of these means, better class separability. Okay, so we have to solve this problem, and however the distance between the projected means is not a very good measure. Well, we could say that only the measure of distance between projected means is not a very good measure. It does not take into account the standard deviation within the classes. That standard deviation within the classes help us to yield better class separability. Okay, so we have to modify our objective function. Now we will modify objective function as a difference between the means normalized by a measure of within class scatter. Okay, no need to worry. This is just seems to be some complex, but it's easy. We will see. Okay, so as a we, our objective function will be difference between the means. Okay, difference between the means. So here we have difference between the means. Okay, this is new modified objective function normalized by a measure of within class scatter. Normalized, we will divide it by within class scatter. So this is the within class scatter. We will discuss this, how this came here to be within class scatter. Okay, we all know about variance. Yes, so scatter is just equivalent term of variance. Okay, so here we have formula of scatter. Although this is scatter, this is defined for projected class. Okay, you can see this over above bar sign. This is in feature space of y. Okay, so here mu is also feature space of y, data points are also for feature space of y, and this is the formula for scatter. Please note this is scatter, not scatter matrix. Scatter matrix is different. So we will calculate s1 square, s2 square within class scatter. This is the with this is a common term in this field. We call it within class scatter. This term is called within class scatter of the projected samples. Okay, so our new objective function is this JW. So what we will be doing with JW? We will maximize JW or minimize JW, or why even this scatter within class scatter is in bottom? Why not in numerator? We will discuss it. Okay, so see, here we have both classes in new dimension. Okay, this is a reduced dimension, and you can see that within class variance is what? This is within class variance. This is within class variance. Class variance of each class. Okay, between class variance, which separates both of these classes. Okay, so we want to increase between class variance. Okay, I think I missed this term. It's called between class variance. Okay, so we want to increase between class variance. So what will be happening? Difference distance between both the classes will be increasing, and we also want to minimize within class variance. So these data points, if we minimize within class variance, these data points come near to their mean. Okay, and these data points come more near to their mean. So we will be having more discrimination between both of these classes, or more separation, distinction between both of these classes. So we have clear cut difference. So we want to increase between class variance. So both mu will be having more distance, and all the data points, and we will be minimizing within class variance so that all data points are as much near as their respective means. Okay, what will be the enhanced result? So first, at first, we were only taking into account mean. So this was our result, and we will be most probably taking our projection on this line. But now we have modified our objective function. So the new result came out to be along this line. Let's suppose if came out along this line, so what we will be having? We will be having as much possible as distance between both the means as max as it possible. So okay, this is so that's why we have within class variance is in bottom. So we try to maximize our objective function. So between class variance is maximized, and within class variance is minimized automatically. So this is the best form. And when we solve, we get some results like this. So you could see distance between both means are as much as possible. Also, we have a clear gap between both the data points. So this is what we want, and we want to maximize this. We want to maximize this distance, minimize this distance, minimize this distance. Okay, so we have to minimize this gap, and maximize this gap so that we have clear distinction between two classes. Okay, so by maximizing our objective function, we would end up with some better result. Summary till now. Okay, so this is the this is just a basic setup of LDA. So what we will be doing, basic idea. This is basic idea. Okay, but note that these things are possible only for two classes, as these things were given by Fisher. So he proposed this idea only for two classes, but later C.R. Rao generalized these for C classes. We will also discuss that. So summary will be, to summarize, what we were looking for all this time was just looking for, so till now we were looking for a projection where the data points from the same class are projected very close to each other. Okay, data points for the same class, data points from the same class are projected very close to each other, and at the same time projected means are as farther apart as possible. Take your time and think about this two points. Okay, data points from the same classes are projected very close to each other. Data points from the same class are projected very close to each other. These data points are as close as possible, and projected means are as far as possible. So first, without any objective function, we were having some result like this. That was just arbitrary result. We would end up with anything. So first problem was that both classes are very near. So we want to separate them. Okay. And we were also having some overlap. This was our problem. And we want to decrease the dimensional reduction. And at the same time, we were wanting to separate both the data points of these classes. So we were trying random lines, and one of those results was this. But for the best, we have to improve our objective function, and at the end result we get this. We have not done any calculation just yet. We have just seen idea. What will it do? Okay. So now this is the maths to the end result. How we will get to how we will get this result. How both these classes will be separated as best as possible. So the math is math to reach the end result. So to find the optimum projection W star. So W star is what? This line. Unit vector along this line is W star. Okay. So we will try to express JW. Remember, our objective function was this. We will try to express this objective function in terms of as explicit function of W. Okay. So we define scatter matrix. Okay. Remember, we have discussed about scatter. This is scatter. Formula of scatter, for this is scatter, but formula for matrix is something different because we don't have a square. We have some matrix into transpose of that matrix. Okay, so we have to make scatter matrices. So this is a formula for scatter matrices, and adding the scatter matrices of both the class give within class scatter matrix. Okay, so we have some new terms within class scatter matrix SW within class. This is the formula, just a normal formula. Okay, so moving from Y to X feature space. See, here all these terms, all terms are in feature space of Y, but we have to take them into feature space of X because we have data points of X and we can work there easily. So we will move to that feature space and scatter of the projection Y. So what we will be doing, we will be slowly converting all these data, all these terms into feature, taking this to feature space of X. And how we will be taking this? So this is as the, let's first start with converting scatter. Okay, so scatter of the projection Y. Scatter of the projection Y can be expressed as a function of the scatter matrix in feature space X. So this is scatter in feature space of X, and we will express this as a function of scatter matrix in feature space of X. Scatter matrix in feature. So this was the formula. Okay, putting values of Y and mu I bar or mu I dash, and we will end up with omega tx, omega t mu I. Solving this, we will get this. How get this? Remember this term. We define this term as our scatter matrix. So we will have this, adding both, we'll be having this SW. SW is just S1 plus S2. Similarly, the difference between the projected means in terms of means in the difference between projected means in terms of means in the original feature space. Okay, so this was our above term. In objective function, above term was mu1 minus mu2. So we'll be converting this, putting values, and now here we have this term. So we will call this term as SB. SB is what? Between class scatter. Just like between class variance, we have now between class scatter. Okay, this is SB. These are just easy calculations you can do easily, very easy calculations. Okay, so finally we have omega t SVW. Now we will put these values in our objective function. We have new objective function. Okay, some things to note here that we are trying to reduce data points from our 2D to some 1D. Okay, so here these both terms are some scalar. Okay, so we will be applying calculus here and we will try to maximize GW. So we will differentiate it and perform calculations. So we will end up with this result. Okay, Mm, and by dividing this term. Okay, so if you solve it, you will end up with this. Okay, so here is something JW. So what is this JW? This is nothing but our objective function. Yes, this is our objective function and it is here again. So see what is JW? JW omega T SB W omega T SVW. So we'll in this equation take this term and divide complete equation by this term. So we will be having this. Okay. Now JW is a full rank matrix. So its inverse is feasible. We will take its inverse, not SB. We will take inverse of SW. And we now have our final equation. Okay. Where J is what? Here J is eigenvalue. Okay. I have said both these are scalar, so don't get confused. J is eigenvalue. W is eigenvector. Okay. W is our eigenvector. From here, we have to find our J eigenvalue. Okay. So do you remember where we started? We started with we have to maximize our G. So what we want? We want our maximum value of J. So we will be going with maximum eigenvalue and corresponding eigenvector will be our line on which we will be projecting our data points. So here is just an example. Okay, this example was also taken in class, but no problem. Here we could again go through it. So we have data points from both the classes x1, x2. We have to perform LDA on that, plotting these data points. We have this graph. Okay, so we have this graph. So solution will be, we will first calculate scatter matrices of both the classes. We will also calculate means of both the classes. Now we will calculate within and between class scatter. You know formula how to calculate this. So SB, SW, both will be calculated like this. And notice that these all are matrices. Yes. So finally for LDA, the generalized solution will be getting by solving this. How we will solve this? So this is just finding eigenvalue. We will calculate this. And finally, we have biggest. We will be getting two eigenvalue here. Okay. But we will be going with the maximum eigenvalue. And this is the corresponding eigenvector. And this is the eigenvector given by LD, which will be our eigenvector, which is having best of both the worlds. I mean, maximum distance between both the means and as much as discrimination between both the classes, between best separability. So now we will be discussing about linear discriminant analysis about C classes. Okay, so we have discussed about two classes which were given by Fisher. Okay, now this will be generalized for C class problem. This was done by CR Rao. Okay, so how we will be generalizing these things for C class problems. So instead of one projection y, we were taking one projection y, we will now see for C minus one projections. Okay. we start with C classes and we can reduce them to at max C minus 1 projections. Okay, so we will be having a lot of Y here. We will make a matrix of them. So we will be having less, no, we will be doing all of them at once. So we will be making matrix of them. So we were having where as many Y by means of C minus 1 projection vectors W, which can be arranged by columns into a projection matrix. So this time we will be also having many W also. Okay. So these will be many W and this is the matrix. We'll be making a projection matrix. Okay. So this is for each projection. We have this. So now this is transformed to this. Okay. Derivation, the generalization of the within class scatter. So how we will generalize within class scatter? Okay. So earlier we were doing things like within class scatter. Okay. We were within class scatter was seen just as the last time. We will calculate scatter for each class and add them to get within class scatter. Okay. And mu I is calculated for each class. This is also same just as last time. Okay. If you want to visualize uh, scatter of each class, so here for red class we have SW1 if, and this is class scatter. So this will be for visual purpose, just for representation. We could assume that it will be representing this thing. Okay. Similarly for other classes. Okay. Now we will be generalizing between class scatter. Okay. So point here to see that we have slightly changed formula for between class scatter. Last time when we talked about between class scatter, we do not have this Ni. Okay. Let us check again for SB. Okay, see here we do not have an item. Okay, but do not worry, we will take this into generalization part. So here we have generalized. For now, I want you that you just remember this formula. We will explain later how this Ni came here. Okay, so one thing is also this is generalized. So if you try to put this formula for that last also, you will get the same result. There will be no difference. The results will be same. So this is also, this is generalized as such, and we will be putting formula here. And this is new term, mu. Mu is overall mean. Okay, mu is overall mean of, we take mean from every class and we just take all mean of all data points, as simple as that. And this could be simply converted like this. So we define new ST. ST is SB plus SW. This is called total scatter matrix. This is just a bit technical term. ST, total scatter matrix. So let's visualize what is SB. SB could be seen at the distance of class mean from total means. The whole mean we have mean of all data points. Mean of all data points and its distance from class mean. And as we will be changing SB, these things will be changing. Okay. So similarly, we can define our whole things mu I. Okay. So this will be vector and scatter matrix for projected samples. Mu. These both things are in feature space of Y. Okay. This is class mean. This is all over mean. And this will be class within scatter matrix. Class. Yeah, between class scatter matrix. Okay. So you could see this Ni. Okay, this will be bothering you, but we will take this later. And just as we derived for our two class problem, we can also write this. Its derivation could also provide, and you can do this on your own also. This is just as easy as that. You can end up with these results. And now Recall that we are looking for a projection that maximizes the ratio between class 2 within class scatter. Since the projection is no longer a scalar, it has c minus 1 dimensions. Since the projection is no longer a scalar. Okay. Now the projection is not scalar and it will be having, this point is important. Recall that we are looking for a projection that maximizes the ratio of between class 2 within class scatter, and the projection is no longer a scalar. The projection is no longer scalar. It has c minus 1 dimension. Okay. Now what we will be projecting those data points into now c minus 1 dimensions or less dimension, not more than that. Okay. So now this is earlier when we were doing projection, those were just scalar projections. Okay. We were doing them on one dimension, but here we are doing them on c minus 1 dimensions and they are no longer scalar. So we will be taking determinant of the scatter matrices to obtain a scalar objective function. We will go for scalar objective function. So we are taking determinant. So we will be taking determinant of both the terms. Okay. So, okay. You could notice one thing also. This could also be written as this. Okay. So here we will put values and we will see the projection matrix W star that maximizes this ratio. We try to maximize this whole ratio. So after solving this, we could easily show that answer will come from solving this equation. Okay, we have to take these, calculate these eigenvalues. Okay, calculate the corresponding eigenvectors. We have to take eigenvectors which are corresponding to maximum eigenvalues. Okay, so it can be shown that optimal projection matrix W star is the one whose columns are eigenvectors corresponding to the largest eigenvalues. Corresponding to the largest eigenvalues of the following generalized eigenvector. Okay, so this is just, we will be solving this equation, taking maximum eigenvalue, calculating eigenvector corresponding to those eigenvalues, and we will be creating new matrix. That will show the optimal projection matrix, and we will use that to project our data points from feature space of X to feature space of Y. Okay, this is generalized for C classes and as tough as to visualize for C classes. So we started with explaining these terms with two classes, then we generalize these things. So now we will talk about how does extra ni appear there. Okay, so the generalization for the between class matrix. This is our new formula. These are terms. So ST is our total class scatter. Okay, total class scatter matrix. So we will try to act. So just this, I try to write this. So it is tough to write in computer like these terms. So we will just like write it like that. It will be easy to manipulate. So T equal to less. Okay. So our T is what? This is our total class scatter. Okay. Total scatter. We told that it is just like variance. So here see, this is the formula of scatter. We will be applying this for whole data points, for all the data points. And here we have W. This is within class scatter. So we'll be applying class scatter for each class and then adding all those scatter to calculate within class scatter. Okay. And this is total class scatter. And we will be trying to calculate what this SB will come. Okay. So here what we have done, we have generalized total class scatter. This is for C classes, okay, within class scatter, and we will try to calculate from this equation what will be between class scatter. So if you try to imagine that we have total class scatter must be comprised of only two terms, within class scatter and between class scatter. There is nothing remain like third term. Okay, as far as my knowledge. So this comprises of SB, SW. So this is a valid point to define it like this. Okay, so we will be applying formula. So here see the first step, xij minus x bar, xi minus x bar. So we have introduced this extra term, which is not a measurable term. We could solve this. Okay, so solving it and then squaring both the sides, we will be having this, applying sigma in the sense we will be applying sigma to go through all the classes and all data points of all classes. So we'll be applying sigma ij everywhere. Okay, here we will be applying sigma ij at this point. We have this, and corresponding for this point we will apply sigma ij on complete term, but as this term has no xj term, so no j term, so sigma j will move inside, sigma I will remain outside. Okay, if you see this, this is just deviation from mean for each class, and we know this term end up with 0 if we don't put mod. You should remember this. Okay, this is from very earlier classes. So this term is 0, so we get rid of this term. We have this. Okay, this is what, this is our t, this this is our w, and we have to calculate these terms. Notice that here again we do not have any term of j. Sigma j will move inside. Okay, this both term will come outside. And for sigma j, if for every class we will calculate sigma j, we will have new term ni. Okay, so I guess this now makes sense. So for writing, we could write it like that: sigma ij for each class calculating this term will result in number of elements in that class. Okay, so this is our new term, and this is exactly b. Okay, scatter means so that t equal to b plus w. So one thing to notice here is this ni seems so simple, but it has some consequences. Okay, we will keep it for another sessions. You can see ni as weight for each classes. Okay, we will cover it sometime later what this means. So I think now you have good idea of everything in LDA, or just a basic thing in LDA, how formulas came up, and when you search on internet, what method you should apply on data points to get the LDA. You can easily get it, but now you know maths behind that, basic intuition behind that. So you could probably do better and know what you are doing when you are applying LDA on data points. Thanks.